Why we use ndir gas analyzer. In our plant, we constantly need to know how much Colorado, CO2, or SO2 is in the processed gas, at the kiln inlet, in the preheater string, or at the cooler. The instrument that does this job for us, day in and day out, is the ndir gas analyzer. ndir stands for non-dispersive infrared. Before we open it up and troubleshoot it, let's understand what's actually happening inside. The whole idea behind ndir is simple. Every gas absorbs infrared light at its own specific wavelength, like a fingerprint. CO2 absorbs at one wavelength, Colorado at another, SO2 at another. If we shine infrared light through a gas sample and measure how much of that specific wavelength gets absorbed, we know how much of that gas is present. The main components of gas analyzer. Let's look at the main parts inside the analyzer bench. First, the infrared source. This is a heated filament, similar in concept to a small light bulb, that emits a broad band of infrared radiation. Right after the source, we have the chopper, a rotating disc with slots. Its job is to break the continuous IR beam into pulses. This is important. It lets the detector distinguish the actual measurement signal from background heat and drift, and it's the reason you'll hear a faint hum or see a chopper motor spec on the analyzer nameplate. The pulsed beam then passes through the sample cell, a tube with mirrored internal walls that the processed gas flows through continuously. The longer the light path through this cell, the more sensitive the analyzer is to low gas concentrations. Some analyzer designs fold the beam path with multiple mirror reflections to increase sensitivity without making the physical cell longer. After the sample cell, the beam passes through a narrow band optical filter. This filter only allows through the exact wavelength that the target gas absorbs. For example, CO2 is measured around 4.26 microns. This filtered beam then hits the detector, usually a solid-state photodetector or a pneumatic detector, which converts the remaining light energy into an electrical signal. How the measurement actually happens. Here's the key to how ndir gets an accurate reading. Most analyzers use two channels, a measuring channel, filtered to the gas we're interested in, and a reference channel, filtered to a wavelength that gas doesn't absorb at all. The reference channel tells the electronics what 100% light, no absorption, looks like right now, accounting for dust on the optics, source aging, or window fouling. The analyzer's electronics constantly compare the measuring channel signal to the reference channel signal. The bigger the difference between them, the more gas is absorbing that light, and the higher the concentration. This ratio is processed against a calibration curve, following the Beer-Lambert law relationship between absorption and concentration, and the analyzer outputs that as a ppm or percent value on the display and on the 4 to 20 mA output to the DCS. This is also why zero and span calibration matters so much. Zero gas, usually nitrogen, tells the analyzer what no target gas present looks like. Span gas, a certified known concentration, tells it what a known high reading looks like. Everything in between is calculated from that reference line. Cross interference and compensation. One practical issue we deal with in the field: some gases have absorption bands that overlap. Moisture, in particular, can interfere with CO and CO2 readings if it's not removed from the sample. That's exactly why our sample conditioning system, the chiller, the filters, the moisture trap, is just as important as the analyzer bench itself. A poorly conditioned sample will give you a wrong reading even if the analyzer bench is perfectly healthy. Many analyzers also apply automatic cross-interference compensation in software, using a correction factor for known interfering gases. But that software correction has limits. It cannot fix a wet, dirty, or leaking sample line. What this means for fault finding. So when you get a suspect reading, think about it in this order. First, is the sample even reaching the cell? Check pump, filters, and sample line for blockage or leaks. Second, is the sample dry and clean? Check the chiller and condensate drain. Third, is the optical path clean? A fouled or scratched cell window will attenuate the beam and read low. Fourth, when was the last valid zero and span calibration? Drift here is often the real cause of a reading that looks off, but isn't a hard fault. And if the analyzer itself flags a fault, like a low reference signal or a chopper fault, that's telling you the problem is inside the optical bench itself, not the process. That distinction alone will save you a lot of troubleshooting time on shift. To sum up, ndir works because every gas has its own infrared fingerprint. A chopped infrared beam passes through the sample, a filter isolates the wavelength we care about, and the analyzer compares that against a clean reference to calculate concentration. Keep the sample dry, keep the optics clean, and keep your calibration current, and this analyzer will give you reliable numbers shift after shift. That's it for this session. See the next video in this series for step-by-step zero and span calibration.